So welcome to the final talk of today. We have Lucia Retore from Dublin, and it's a pleasure to introduce her. She is, I guess, a newcomer to AdS2. It's her first time in AdS2, and is also, I would like to point out to the organizers that it's very good that you in the end you stuck to this other tradition of AdS2, that you have a lot of many young speakers. That's wonderful. And Anna is certainly one of them, and we are very much looking forward to your talk.
Thank you very much. So thank you very much for the organizers to invite me. I'm very happy to be here, and my first time at AdS2. So today I will talk about lifting integrable models and long-range spin chains. So there are many applications of integrability, as we all know, especially in string theory. We have many of them. And in recent years, many new ones appeared in condensed matter in particular, like these open quantum systems. There is some systematic construction now for them. Also in quantum computing, they are starting to try to do a few things. So there are new applications also appearing. And we have this huge box of tools that integrability provides. And in the recent years, this box of tools has been increasing as well. Like we have now quantum spectral curve, hexagons. So we have many nice techniques that we can apply to integrable models and many nice applications. So I believe the questions to be able to reply, like to look to a Hamiltonian and to say if it's integrable or not, remains a very relevant question. To be able to classify integrable models with a certain ansatz is also a relevant question, and also to be able to systematically construct new integrable models. So this is what I will talk about today. And of course, there are like a lot of work has been done on this subject. For example, the algebraic method is by far the most successful to find the integrable models. Like lots of models were classified in this way, in a very systematic way. And in particular in AdS CFT, most of the matrices that were found people used this method. And a very important part of this method is to have a symmetry, like Yangian, for example, then you can use it. And but you cannot apply it if you don't have a symmetry. So there are some limitations. But if you can apply it, it's very nice. You can solve linear equations to find your matrix, so it's very effective. There are some other methods, just to cite a few, like you can directly diagonalize the Yang-Baxter equation by applying a derivative on the equation and solving some differential equations. This can be quite hard for some classes of models, but you can do for a few classes. You can also expand their matrix and try to sum at some point, like in terms of, you can expand in terms of the spectral parameter and the Hamiltonian and try to sum at some point. And these are all very nice. They all have very good advantages and a few disadvantages. And today I will present two different ones. And they also have some advantages in comparison with these and some disadvantages. And I'll try to argue why they are interesting and useful. So the talk is divided mainly in two parts, like the two methods we will use. The first is this boost automorphism method. This is about a project with a few projects with Marius, Chiara, Anton, and Paul at Trinity. And this is applied, it can be applied for nearest neighbor spin chains. The second method will be able to apply for long-range spin chains. It can actually be very easily applied for long-range spin chains. And I will show two examples. We computed the three-loop lax operator and the R matrix for the SU2 sector of n equals to 4 superring Mills. And they arranged 3 6-vertex deformations using this method. This is a project I did with Marius at Trinity. Okay, so let's start with the first method. So this boost automorphism method. So the goal here is classifying integrable models that satisfy regularity. So when you have that both spectral parameters are equal, you have the permutation. And you want the logarithmic derivative to be your Hamiltonian. And we will consider, for the purpose of to classify these models, the periodic chain. So nearest neighbor interaction, a periodic chain. So it's very relevant to do this distinction of difference and non-difference form for our method. So difference form is usually when you can write your matrix as R of the difference of the spectral parameters. All the relativistic models are in this class, and if you have this type of our matrix, your Hamiltonian is constant. This is because of how this is defined. So your Hamiltonian will not depend on the spectral parameter. And the second type is non-difference form. And this means that you cannot write the R as depending on the difference of the spectral parameters. This case is usually much harder to classify just because it's harder to solve the Young-Baxter when you have this structure. There are not so many models known in comparison with the first class. But the ones that are known are extremely interesting, like Hubbard model is in this class, for example, and the AdS models, like in AdS2 and AdS3, they're all like this. So it's useful to be able to classify them. Okay, so let's say we start with some ansatz Hamiltonian. I just put some 6 vertex here just to exemplify, and let's say, so for now we are saying that it's depending on U. So, oh, I forgot to say, so here, if our matrix is of non-difference form, your Hamiltonian will depend on the spectral parameter, so it will not be constant anymore. So, well, let's say we start with some ansatz Hamiltonian, and we want to be able to say if it's Young-Baxter integrable or not, or if you want to classify all these, the Hamiltonians with these ansatz that are integrable. Of course, for these ansatz we know, but it's just an example. We actually found some interesting things even here. But, okay, so we want to solve Young-Baxter. Let's say we start by applying a derivative with respect to U, and then we send V to U. We could, in principle, try to solve this. It's very hard, is that method I mentioned before. But we could also put these conditions we know here, these conditions we assumed at the beginning, and we will get what's called a Sutherland equation. And let's say we would like to solve this equation. The hard part here at this moment is that we don't know the Hamiltonian and we don't know the R. So we have these differential equations with too many unknowns. It's especially for non-difference form, it's very hard. So the ideal would be if we knew what this Hamiltonian is, what this Hamiltonian could be. If we had some clue, like some hint about the Hamiltonian, we could do much more. It would be much easier to solve. So the question, like, do we have an independent way to solve to say if this H is integrable, or let's say if we can put some extra conditions on this H from the beginning. And for that we can use this boost automorphism mechanism. The boost is very nice because you can use it to generate higher charges starting from a smaller charge. So if you have a charge like QR, you can generate QR plus 1 just by commuting with the boost. So this is very useful. So you have a kind of an independent way to construct your charges. So what we do here, the first step is like we start with some ansatz and we generate Q3 using the boost. And then the first step for integrability is that Q2 and Q3 have to commute. So here, if you want to classify the difference form case, we can start with a constant Hamiltonian. And then to solve this equation is basically to solve a system of cubic polynomial equations. You can put on Mathematica and solve it. And if you're interested in non-difference form, you have now a derivative that will contribute here. And because your Hamiltonian is U-dependent. And you have to solve now a system of differential equations instead of just the cubic polynomial equations. But let's say we did this. So we now have some Hamiltonians that are potentially integrable. So they satisfy Q2 with Q3. So, but in principle, we need all the other commutation relations being satisfied, not only Q2 with Q3. But let's for now to assume that Q2 and Q3 is enough. and substitute it on the Sutherland equation. So we did that for several classes of models, and then we solve it for the R matrix. So when you do this, it's much, much easier than before, because now you just have to solve these differential equations, the system of differential equations for the R, not for both R and H at the same time. And actually it was enough. So Q2 with Q3, so for all the systems we tried to classify, Q2 with Q3 was enough. We never found an extra condition on the Hamiltonian. So we always managed to find an R matrix just with the conditions that we had found from the Q2 with Q3. And this is actually quite under control. So you can, even for non-difference form models, it can do a lot actually. So it's quite nice. We're quite happy about it. So the summary of the idea is that we start with some ansatz for the Hamiltonian. We compute Q3 using the boost operator. And then we require that Q2 with Q3 commute. We solve this system of polynomial order of differential equations. We find these potentially integrable Hamiltonians. We can just substitute this on the Sutherland and find the R matrices, and then we check. So this was applied for many cases. So at the original paper for difference form, Marius, Paul, and Anton, when they did the first paper, they applied and they found all 4x4 difference form models. They managed to classify all of them. And then on the we classified these SU2 plus SU2 R matrices for both difference and non-difference form. And for this case, you find several new non-difference form models, and all the ones that were known. We also managed to find the new integrable deformations of AdS2 and AdS3 S-matrices. And this includes an elliptic deformation, which is quite interesting. Like it's an elliptic deformation that interpolates between AdS2 and AdS3. So you have some elliptic function. It depends on elliptic functions, and when k goes like the modulus of the Jacobi functions, when the modulus goes to 0, you get AdS3. But when the modulus goes to infinity, you get AdS2. So it's quite interesting. But also, Marius, Chiara, and Balázs applied this method for Lindblad systems. So these systems, you take into account also the contribution of the environment. So they have, so there were several cases that were known to be integrable for these Lindblad systems, but there was not a way so they were always checked to be integrable, like some known model was, but this was, they did the first systematic construction for these systems. So the method seems to be nice. So we managed to, for the ansatz we managed to find all the known models that should be there, and several new ones. And it's relatively easy to apply. So when you don't have much symmetry, you can still apply it in comparison with other models. And it's particularly effective for non-difference form. So in principle, we are very happy. But there are some disadvantages always. So what we expected when we started was let's classify the models, and let's say we find a few interesting solutions. What happened in practice was that we found lots of dependent solutions. And this is because you can transform the R matrix in certain ways, and this will preserve Yang-Baxter. So there are several types of transformations you can make on the R matrix that would preserve Yang-Baxter. And we have to find a way to distinguish this, and the method generates lots of dependent solutions. So we need, and you can kind of apply these transformations in different orders. So it's quite hard to, for simple models, for the cases we solved, they were quite manageable. But if you try to put, to crowd the R matrices, or you can, at some point you start to have a technical problem to how to distinguish this. So it's a lot of work to make this distinction and separating groups and say, just keep one. A second disadvantage is that, okay, we are trying to, if somebody gives you a Hamiltonian and asks you, is it integrable? And this Hamiltonian they give you is constant. Sometimes you try and you say, oh, it's not integrable. But it could be that when somebody gave you the Hamiltonian, they had chosen, like for some physical reason, the value of u was chosen. And this Hamiltonian originally was, like, there exists a Hamiltonian that will be integrable, but it will be u dependent. But you don't know that because somebody just gave you a constant Hamiltonian. So you would reach the wrong conclusion for these cases. So this is a problem. And since we don't have this u dependence, so for small cases you could try to put an ansatz and classify, you'd have to classify all the cases of that structure to be able to see if the particular one is there. So if you need something that's a bit larger, this becomes very hard to do. And the third problem is that we were not able to generalize these for long-range spin chains. So this brings us to the second method, so where we try to solve these problems. And the main question we want to solve here is if somebody gives you a constant Hamiltonian, can I say if it's integrable or not, independently of if it could be u-dependent at some point or not? The answer is yes, and I will explain now why. So it's well known that you can define your transfer matrix as this product of lax operators. And then your charges are just, for periodic chain, they are just the logarithmic derivative of the transfer matrix. And you have this RLL equation, so all this is very standard. So for the method, we will start now like always with a constant Hamiltonian. So I put here this example is just some 6 vertex Hamiltonian, like 5, like this, yeah. It's still nearest neighbor at this point, so I will explain the method for nearest neighbor first, and then to say how it is modified. So we still consider periodic chain and regularity, but always constant now. So the way we start is like we expand the lax pair like this, in such a way that you will have the Hamiltonian here, and we put this like everything explicit, all the u dependence is explicit there, so all these Li's are all constant. So we'll take this expansion. So it's something very simple. We were taking some expansion. We are putting on the transfer matrix, and we are computing the charges. So the first thing we compute the Hamiltonian, and then we compute Q3. So, but we will always keep only the first term, because if we want Q2 with Q3 commute, this term will always commute already with Q2, so it doesn't contribute. So it's just much easier to do the method very fast for many orders if we forget these terms, because they never will contribute. So, because they are not relevant for the commutator. So for this specific model that I put the example, if you solve this, you get only one condition. So at this, from Q2 to Q3, so if you remember here, we had 6 objects here, and only one of them is fixed by Q2 with Q3. If you go one more order, like if you compute Q4 now, like this, ignoring all the rest of the terms, and you require it to be 0, you again can find a condition for L6. And if you keep going, you can always solve for this L6 element and forget the rest. The other ones are free. So you can basically choose them. So you can keep doing this, and like you fix, like when you commute Q2 with Q5, you fix L6 4. And if you do Qn, Q2 with Qn, you get L6 n minus 1. And all the crossed ones, like Q3 with Q4, they're all automatically satisfied. If you satisfy Q2 with, like we check it, then they're all satisfied. So what you do now, like this is very easy to apply for, like we managed to get like 20 charges in minutes. It's very computationally easy. And then now you have to make a choice, like you can put all the ones to 0, or you can make a choice that's efficient for you, but you have to sum the series you got for L6. So you got something, some results for L6, and you have to sum this series. And for this case, it's very easy, but I will soon show a different way. So the advantage of this for the cases we did so far was that we didn't get this crowd of solutions. The method seems for, like, we did very few cases so far, so I don't want to make a too strong claim. I don't know if this solves completely the problem with the dependent solutions. But so far it seems it already gives us something separate and nice. And the extra dependents are like all these free functions we have on the LAX. So they encode all the types of basis transformations and things you could do. In principle, they are there. So, and you can kind of choose these extra ones to have something nice or something that is more interesting, depending what you want. But depending on the model, it's not easy to sum the series. This is what we realized. It can be quite tricky to sum the series. So what we actually in practice did for all the examples, even in long range that I will explain later, was that if you put these extra ones to 0 from the beginning, you see that you have some elements that are very simple. And then especially for like here it doesn't make much sense because you would put them to 0, but in the long range it will make more sense. You can put all the simple ones there, and then you have just 1 or 2 complicated ones, or 4 or 5 depending if you have a larger AdS or something. And just by computing the transfer matrix with the Hamiltonian, if you have few of them, you have something linear to solve. So these things that are extremely hard to sum, you just get them for free if you compute the transfer matrix with the Hamiltonian. So it's a nice trick, I think. And once you can find the LAX, you can just find the R matrix by solving RLL. It's linear, so you can do it quite quickly. So the advantages are that, so with these, you get a non-difference form R matrices for free, or like the difference form ones. You don't need to specify like to start with a Hamiltonian that's you dependent to get them. So automatically you should, if your model is regular, which was something we required at the beginning, you should be able to say if your model is integrable. So it seems more efficient in terms of not generating all these dependent solutions. But the thing we were quite happy about is that it's kind of easy to apply for long-range spin chains. With this trick of commuting with the Hamiltonian, so you solve a few orders, you see which ones you can put to 0, and then you can kind of do just commuting the transfer matrix with the Hamiltonian, you can get the rest. Okay, so yeah, just saying a few things, but that we all know. But yeah, in the context of AdS-CFT for planar n equals to 4 at one loop, we know that the dilatation operator can be related to the integrable nearest neighbor spin chain. And at each order in perturbation theory, the interaction range of this Hamiltonian increases. So you have something like at one loop is nearest neighbor, 2 loops is like nearest next to nearest neighbor, and so on and so forth. And the full Hamiltonian will have like an infinite range. Like some framework, a framework to deal with this type of spin chains was put forward in 2008 for the charges. So they can perturbatively get the deformations for higher range. And it was later used to classify the integrable long-range deformations of the 6-vertex model. And what we would like to do now is like we would like to to apply this for the Hamiltonian of the SU2 sector in n equals to 4 spring mules. So we'd like to see if we can get our matrix and the lax operator for like 2-3 loops. And we would like to see if the range 3 deformations that was on their paper, like for the charges, if they are Yang-Baxter integrable, in the sense if we can get the R matrix and the lax for them, and if all of them have like a lax in an R matrix, all the deformations. So these are the 2 questions I have to reply. We would like to reply. How much time do I have? I don't know if I'm going too fast or too slow. Okay, thank you. So to do this, we need one more ingredient. So last year, Tamás and Balázs put a very nice paper for that Tamás explained this morning as well, with these medium range spin chains. And they kind of realized that if you increase the dimension of the auxiliary space, you can use this to get long range deformation, like these longer range deformations in comparison with the nearest neighbor, like this finite long range. So for range 3, for example, if your physical space has dimension d of v, the dimension of the auxiliary space, you put the square. And then you can do many things, so we will use this here. And so for range R, what we do is like the dimension of the auxiliary space is the dimension of the physical space to the range -1. And we didn't consider wrapping, so if you're interested in wrapping, Tamás also explained many nice things this morning, and you can look a bit more at his paper, but we will avoid. So to avoid wrapping, we are always doing all the calculations for L at least equal to 2 times the range. Okay, so if we start with the Hamiltonian for SU2, we have this type of Hamiltonian, and so for integrability purposes, you can consider the second line is the same thing as the first line, since you're just shifting by identity. It's very easy to put back on their matrix this, so we are just considering the second case. So what we do is, again, we just follow our procedure with the expansion, and we'll put on the transfer matrix, again, like we did before, but now we will solve perturbatively to each order in G. So if we consider 2 loops, it's very, very easy because you just have one function to fix at the end. And we are requiring always these boundary conditions, so we kind of have all these regularity conditions are still here in the Hamiltonian. So you expect to recover the Hamiltonian here. So this case was very nice and simple to solve, and then we got both the lax and the R matrix for this 2 loop. The R matrix you can get just by perturbatively solving RLL. And then the next thing we decided to do was like try to do 3 loops. So these are the SU2 invariant objects you can put here. So we put these rows, and we apply the method. So we have to solve perturbatively up to G to the 4th. And we find some conditions. So these A's are in front of the sums here. We found some conditions on them. So here it's depending on A1 and A2, basically. And if you consider, so if it doesn't satisfy these, it's already not integrable, even perturbatively. And then considering that's symmetric, we have 2 deformations, but one is just a Q4. So it's something of range 4, what you have like is Q4, in this case, one of them. So it's one proper deformation. But I'd like to highlight that we cannot put all the A's to 0. So even if you were not thinking in n equals to 4 superior mules or anything, if you truncate, this spin chain is not integrable. Like it's perturbatively integrable, but if you don't have the option to put all of them to 0. So if you have this range 3 deformation, this G squared, you have to keep putting. You have to put at least G to the 4th. And this kind of matches with the result by Anna and Tristan, where they found chaos when they look at, they took up to 2 loops and they studied the model and they found chaos for this model. So it shows that like the truncated model is not integrable. So we found explicitly the lax, and we found the R matrix, but there is no chance I can put it here. It's really, really huge. And because of that, so if you look here, you still have some lambdas. So you have that freedom I mentioned before that you keep. Like, so here we kept this freedom, and you, in principle, you could think that they are completely free. For this case, they are not because of the boundary conditions. So if you expand on U like this, what you get some conditions you have to satisfy. And okay, I already mentioned the R. So we have both the lax and the R matrix up to 3 loops, and it would be nice to continue. It gets a bit harder computationally because since you need to keep increasing your auxiliary space, it becomes quite hard. But for these cases, we have the explicit formulas. And then the next question we'd like to solve is to answer is that if those deformations of those range 3 deformations computed for the charges, if they're all Young-Baxter integrable. So we put this constant Hamiltonian, it's the same they have. We added the range 3 Hamiltonian here. And so since it's 6 vertex, the only condition we put is that the total Hamiltonian has to commute with the total spin operator. And we apply the method again. We put the expansion of the lax on the transfer matrix. We solve it perturbatively for so order 0 and 2 on G. And we found the lax and the R matrix. But the main result here is that all the range 3 deformations they have an R matrix associated to them. So all of them are Young-Baxter integrable. And this is quite non-trivial, I think. Yeah, so it seems quite smooth to apply the method for long range. So there are quite a few things we think so we really can we can try to start to generate a perturbatively long range models that could be interesting. But I think also one of the main points for us is really this to be able to reply if the model is integrable or not. I think this is something we really wanted because we were really we were trying for a bit. So there are several future directions we could take. So we are really hopeful somewhere to find some functional way to write some closed formula for the lax and the R matrix. So if you just keep doing order by order, you find larger and larger objects. So we would like to find a way to factorize nicely these extra terms in a way that maybe we can see something, but we don't know yet. It would be nice to have this at all orders. Also now if we could apply to some physically interesting models, if anyone wants to try to get a long range, that could be interesting for many areas. And something that would be nice as well is in this paper with Anna and Tristan, they found that was chaotic when they truncated, but it was weakly chaotic in the sense that the crossover to the chaotic dynamics was it was lower than the generic chaotic model. So it seems that somehow the model remembers that that was integrable if you keep more. So something we're thinking is if you could take some simple models that like some nearest neighbor models that very simple, and try to get a few deformations and truncate and see if this is a behavior that's always there. Like if you do the same calculation, if it will be chaotic, weakly chaotic as well. So to see if this is something that was just an accident for n equals to 4 superring mills, or it's something that's a a feature of these models that when you truncate, the model kind of keeps some memory of what happened. And thank you. Yeah, that was.
Questions?
Can you please show Sutherland equation?
Yes.
So, assuming if I assume that H is known,
Yes.
how many equations is there and how many variables?
All the ones that will be in your ansatz for R. So it depends how big is your model. Like you have.
No, so let's say R is n by n matrix. Then it is.
Sorry?
So.
I didn't hear. It's a matrix, like they're a matrix. So you start with some ansatz for the Hamiltonian, and let's say you know the Hamiltonian, so now you have a Hamiltonian, it's a matrix. You have to find the R, so you put an ansatz for the R, and you have to solve the equations to find all these elements on the. So you have a system of differential equations that they couple more and more depending on how crowded is your R matrix. So it becomes a bit harder if you.
So there are more equations than variables, right? Yeah. That's true. There's more equation than variables. So, but what happened is that for each case we found a unique R that, which makes sense, I think.
Further questions?
So parts of these long-range models that you look at, those that you can get by deformations with the higher boost operators are equivalent to inhomogeneous spin chains with inhomogeneities depending on the coupling constant, the deformation parameter. Maybe there could be some map between your Lux operators and Lux operators of inhomogeneous spin chains that exploits this relation. Yeah, it's probably more a comment than a question.
I'm not sure if at the very beginning I didn't hear what you. Sorry, could you repeat it?
Okay, these long-range models that you consider, parts of them, those that you get from deformations with these higher boost generators.
Yes.
They are equivalent to inhomogeneous spin chains where you have the inhomogeneities as functions of the coupling constant of this deformation parameter. And for those you can also write down Lux operators, right? So
yes.
I'm wondering if your Lux operators somehow factorize into these inhomogeneous Lux operators that could maybe
it would be nice
be observed.
Yeah, I don't know, but it would be nice to see that.
Thank you.
So 2 questions from Ryo Suzuki, but I think the second question was about inhomogeneities in the L operator, so I think it was answered. But the first question is this classification method doable for large dimensions?
Yes, you can apply for larger, like in some, like, do you mean just starting with a Hilbert space of higher dimension? I don't see why not. You could start with, okay, the first or the second method? Actually.
So yes, there is a parenthesis here, spin S x x x with S greater than 1/2. The matrix dimensions of Limlandian is a square of Hamiltonian. This is Rio's question. Yeah. Is this classification method doable for large dimensions? Yes, but I cannot have a feedback.
For large Hilbert spaces, yes. So basically the conditions we put here were regularity, and that should reduce to the Hamiltonian. So if it's in this class, I don't see why not. And the expansion, I also don't see why it would not. You're just expanding and putting on the. So I don't see why it would not work.
I see no further questions. We had quite a few questions along the way also. I think I'd like to close the session, but I would also like to thank Anna one more time.
Thank you.